So, Lecture 4.5, Multivariate Probability and Correlation. Thus far, we have considered probability, density, and mass functions of only one random variable. But, of course, often we measure multiple random variables, x1, x2, through xn, during a single event, meaning a measurement consists of determining values x1, 2, through n of these random variables. We can consider an n-tuple of continuous random variables to form a sample space, omega equals Rn, on which a multivariate function, f, called the joint probability density function, assigns a probability density to each outcome, x in Rn. The joint PDF must be greater than or equal to 0 for all values of x. The multiple integral over omega must be unity, and the multiple integral over a subset of the sample space A is the probability of the event A. We can consider an n-tuple of discrete random variables to form a sample space on which a multivariate function, you can index the sample space with the natural numbers, of course, which a multivariate function maps to the reals called the joint probability mass function, assigns a probability to each outcome in the indexed space. The joint probability mass function must be greater than or equal to 0 for all x, and the multiple sum over omega must be unity, and the multiple sum over a subset of the sample space A is the probability of the event A. So it's very similar to probability density functions that are not joint, they're just single variable, but these ones are multivariable. Let's visualize multivariate PDFs by plotting a bivariate Gaussian using MATLAB's MVN PDF function. So we'll define means 10 and 20. We'll define, so these two variables, a mean for the first variable, a mean for the second variable. The covariance matrix, we'll talk about the covariance in a few moments. And then we generate here vectors using linspace, which are essentially going to be plugged into the MVN PDF function to generate values over. So these are giving us the vectors over which we want to define our variable to plot, our function to plot, and we'll plot it. Ooh, it does not come out very nice looking in Illustrator, but if I go over to this representation here, oh, it's nice and pretty. So we have random variables x1 and x2 with the means 10 and 20, and we've got some probability density function over it that we're plotting. So that's, you can see that if you were to integrate over some region of this, you would get the probability of the variables both being in that region. Okay, so that's our two-variable Gaussian PDF. Marginal probability. The marginal PDF of a multivariate PDF is the PDF of some subspace of omega after one or more variables have been integrated out, such that a fewer number of random variables remain. Of course, these marginal PDFs must have the same properties as any PDF, such as integrating to unity. So we'll do this with the bivariate Gaussian using the MVN function from above. We're going to just continue where we left off. Let's demonstrate this by numerically integrating over x2, which will give us the marginal probability density function, or marginal PDF of x1. Given that x2, we've integrated over all of x2. So we'll use the TRAPS function, trapezoidal integration, and I'll just plot it. It's a little rough. I probably should have taken more points, but this is the marginal Gaussian PDF, which looks like this, which has the mean. This is x1. So remember, x1 is this variable. x2 is this one. So we integrated over x2, and we got just a variable in x1 that remains. That's our marginal PDF. Okay. We should probably verify this integrates to 1. And if we take the traps again of that function over x1, we get very close to 1 as our probability, which is pretty close. I mean, we didn't do a very careful job in our numerical integration, and so getting that close to 1 is actually a little surprising, but not too bad. Okay, covariance. Very often, especially in machine learning and AI applications, the question about two random variables, x and y, is how do they covary? Like, how do they vary together? Do they have a relationship between them that is what we will call correlated in a moment? That is, what is their covariance, defined as being, so we use this notation, cov of x and y. It's the expected value of the product of the random variable minus the mean, and I could have used m there instead of mu, but that's our sort of two notations for the mean, m or mu, x. So the difference between x and its mean, and the difference multiplying the difference between y and its mean. This simplifies to this expression below. Note that when x equals y, the covariance is just the variance, right? The variance was just expected value of x minus its mean squared, so which is what this reduces to. When a covariance is large and positive, it is an indication that the random variables are strongly correlated. When it is negative, or it is large and negative, they are strongly anti-correlated. Zero covariance means the variables are uncorrelated. In fact, correlation is defined as being the covariance divided by the square root of the variance of each of them multiplying each other. This is essentially the covariance normalized to the interval -1 to 1. So the correlation is just the covariance normalized, and that's a really nice thing to see. So we're looking at covariance as being, or correlation as being something that measures, they both measure the how similar two variables are to each other. Okay. Sample covariance. As with the other statistics we've considered, covariance can be estimated from measurement. The estimate, called the sample covariance, Q, of random variables x and y with sample size n is given here, where you just take the differences divided by, or subtracting out the sample means, and you sum up the product. So very similar definition to what we saw before for the sample variance. Multivariate covariance. When n random variables xi, with n random variables xi, one can compute the covariance of each pair. It is common practice to define an n by n matrix of covariance called the covariance matrix, sigma, such that each pair's covariance is the covariance of xi and xj. So the covariance of xi and xj is denoted like that. And it appears in its row-column combination, making it symmetric, as shown below, because the covariance of xi, xj equals the covariance of xj, xi. So we get the covariance of x1 and x1, x2 and x2 on the diagonal, which means that we've got, these are the variances, right? And then the covariances are the off-diagonals. The multivariate sample covariance matrix Q is the same as above, but with sample covariance is QXI, XJ. Both covariance matrices have correlation analogs. So you can also do a correlation matrix as well. So car data, sample covariance, and correlation. Let's use a built-in multivariate data set that describes different features of cars listed below. So MATLAB's got this carsmall.mat that comes with MATLAB. It's a nice little data set. Some of the variables are correlated and others are not. Some of them are anti-correlated, as we'll see. Let's compute the sample covariance and correlation matrices. So we have miles per gallon, cylinders, displacement, horsepower, weight, acceleration, and model year as our variables. We have n of them total, and we're going to see how long is each of these. You take just one of them and find the length. That's what m is. So we pre-allocate the data. We're just going to populate it with the variables, and then we can do the covariance matrix, the sample covariance matrix, using NaNcov. We're using Nan because we want to continue to compute the covariance even when there are some not a numbers in the data. This is something that is convenient because if we have an incomplete data set, which is very frequent, there will be some not a numbers that will show up. If you don't use NaNcov, your covariances will come out to be nans, not a numbers, which is not really what you want. You want to go ahead and do it and ignore the not a number elements. So, and to do the correlation from the covariance, you can use this corcov function, and it gives you the sample covariance or correlation. This is highly correlated, anti-correlated data. Let's plot each variable versus each other variable to see the correlations of each. We use a red to blue color map to contrast anti-correlation and correlation. Purple then, right in between red and blue, is uncorrelated. The following builds the red to blue color map. So we build up the color map, and then we do the plots. So it creates this array of plots, which is slowly coming into our screen here. Okay. Very slowly. Okay. Don't know why things have become suddenly very laggy, but hopefully this is still recording. Okay, so I think it's done being really laggy here. Probably should have rasterized this graphic. I think it's the graphic is giving my graphics card a run for its money, but slowly coming into view here. So how to read this is to say, okay, each variable is going to be strongly correlated with itself, of course, right? And so you're going to see that covariance relationship with itself being perfectly correlated. You're going to see other variables that are anti-correlated, which they have negative slopes associated with them here. And when you plot them versus each other, and you see those show up in red, the correlated things are in blue, and the things that are not really correlated at all, so not anti-correlated and not positively correlated will show up in purple. So we see the purple clouds here. They don't really have a correlation at all. And it's also symmetric. So you see these plots showing up that are symmetric to each other here across the diagonal. Okay, so this is the way that we represent data that's correlated or uncorrelated, and testing to see, are these things correlated? It's an easy way to visualize it. Okay, so I'm just going to try to stay away from those plots because they freak out the graphics card. So conditional probability and dependence. Independent variables are uncorrelated. However, uncorrelated variables may or may not be independent. Therefore, we cannot use correlation alone as a test for independence. For instance, for random variables x and y, where x has some even distribution and y is the square of x, clearly the variables are dependent. However, because one literally depends on the other, however, they are also uncorrelated due to symmetry. So let's do that. Let's take a uniform distribution, and we'll have x be a uniform distribution and y be the square of that distribution, of that sample, and we just essentially compute the correlation, and we find out that if you take the sample size to be large enough, the absolute sample correlation goes to 0, okay, which is what we expected. It is that they're actually not correlated, and yet we started out with a data set that was generated from the other data set. So y is generated from x. It depends on x, so they are dependent. They're not independent, and yet their correlation goes to 0. So that's one sort of demonstration that you have to be careful, because not being correlated does not mean that that those variables are independent of each other. Okay, so that's the entirety of this lecture on multivariate probability and correlation. It included a lot of the concepts. It was a bit of a whirlwind tour, but hopefully it's got all of the main things. You can compute your covariances and your correlations, and you can represent them, and you can see this is actually one of the fundamental ways that machine learning is done, is using these sorts of correlations and covariances. So one of the first things.